Applications of integration. So we've already applied integrals a little bit, knowing integrals represent the area between a curve and the x-axis, or applications in respect to a certain context, taking the integral of something is the antiderivative. So chapter 6 focuses on, or rather the sections we focus on are being able to find area between curves, that's 6.1. Being able to find volumes of solids, that's 6.2, and then 6.4 is using an integral to find the average value of a function. So those are the three things that chapter 6 covers. So for 6.1, so talking about area between curves, I'm going to talk about this in the general sense first. So on this diagram here, if you consider the region S, it lies between two curves. So we have y equals f of x and then y equals g of x. And also between, so we're on the closed interval from A to B. So it's restricted by these vertical lines, x equals A and x equals B. F and G are both continuous. In this respect, f is greater than or equal to g for all x in that closed interval. So the idea is we want to find the area of that region S. So talking about this, how we first started out chapter 5 with finding the area that was underneath a curve but also bounded by the x-axis. Here our two bounds are two curves, not just the x-axis. So if we divide this region into n strips of equal width, so this is getting back to the idea of approximating rectangles, and we approximate the ith strip by a rectangle with base delta x, and then this would be how you would calculate the height. So if I called, let's just say at this x value, when they use the x sub I star, just remember that represents a sample point, so it could be the right end point, it could be the left end point, it could be the midpoint of an interval, it could be any x value within a certain interval. So you're taking, I'm just going to draw one approximating rectangle, but that's what this is talking about. So you're dividing S into n equal strips and finding the areas of those rectangles to approximate it. Each width would be delta x, which is still your b minus a divided by n. But then the height of that rectangle, or the length of that rectangle, is the y value of f of x minus the y value of g of x. It's that distance between f and g at that x value. And that is explained here. So the height would be f of x sub I star minus g of x sub I star. And so just like we did at the beginning of chapter 5, so they give the Riemann sum from the I value 1 to n of each rectangle. So basically you're taking all of the areas of the rectangles, adding all of those areas together is an approximation to what we intuitively think as the area of S. We know from chapter 5 that approximation will become better and better as your number of rectangles increases, so as n approaches infinity. So we define the area A of S as the limiting value of the sum of the areas of those approximating rectangles, which is written here. So then we recognize this limit as an integral. So this is how they define the area between two curves. So the area A of the region bounded by the curves y equals f of x and g of x, and the lines x equals A and x equals B, where f and g are continuous, f is greater than or equal to g for all x in the closed interval, is the integral from A to B of f of x minus g of x dx. So the area between curves is the integral of the difference of those two curves. And this is kind of the y listed up here where that integral is coming from. So today is just practice using that. So when you are given, for example, 1, the area of the region bounded by y equals e to the x, y equals x equals 0, and x equals 1. Here's your A and your B. But you would have to figure out on the interval from 0 to 1, you need to know which curve is on top and which curve is on the bottom on that interval. So it might require, if you have your graphing calculators, I'll show mine so you can see it. I usually will start out, if they don't provide a graph for you, graph the curves you are given on the interval you are given. So we have y equals e to the x and y equals x. And I'm going to change my x min and max to 0 to 1. I'll leave the y min and max for now. So here is e to the x, that is graphing first. And then y equals x on mine graphed in red. So again, what you want to be able to tell from graphing this is you need to know which is the top curve, which is the bottom curve. So if you were to actually draw a rectangle in this region, you need to know the height of the top of the rectangle and then the bottom of the rectangle so you know how to set up your integral. So actually, I'm going to add that into this definition as well. Just make sure your f of x is the top curve, your g of x is the bottom curve. Okay, so according to that graph, y equals e to the x was the top curve, y equals x was the bottom curve. So here's the integral we would set up to find the area between those two curves on the interval from 0 to 1. We would have the integral from 0 to 1 of the top curve, which is e to the x, minus the bottom curve, which is x, and then dx. And then you would just evaluate that integral. Okay, so if we evaluate this integral by hand, how do we do that? Antiderivative. So we would have antiderivative of e to the x evaluated from 0 to 1. So substitute 1 in first, and that would give us e to the first power. Keep it in exact form as well when you're working through these by hand. Keep it in exact form. So e to the first, which is e, minus 1/2 times 1 squared is just 1/2. So e minus 1/2 is what we get if we substitute in 1. And then minus, if we substitute in 0, e to the 0 is 1. And then that's just minus 0, so we just get minus 1, basically. I'll put the minus 0 so we know it's there. So altogether, we have e minus 1/2 minus 1 would be minus 1.5 or minus 3/2. So this would be the exact value of the area between those two curves on the interval 0 to 1. Questions on that one? Was this how you had to do it? Like antiderivative wise? I mean, it was indefinite, so in some way you needed to know an antiderivative or find one. Not right away. Yes. Well, you could have done it that way. Split it into different fractions. Right. As I said, there was a reason it was extra credit. It wouldn't have been a fair one for me to just put on the regular part of the test. I didn't look at what anybody did for it, though. What anybody tried. Okay, for example 2, so I just put 3 examples where just some different things may be required. So the main part of today, you already know how to evaluate an integral. It's making sure you set up the correct integral. So example 2 says to find the area of the region enclosed by the parabolas y equals x squared and y equals 2x minus x squared. It does not give you A and B like the previous example did. So if it says the region enclosed by the parabolas, that must mean these parabolas intersect, and you need to find where they intersect. So I'm going to graph these 2 parabolas, x squared and 2x minus x squared. I'm just going to change my window to the standard window. Yeah, you could. So you can, if you're in the standard window, the region is very small, but you can see that they do intersect twice, and they create, you're finding the region that's enclosed by the 2. So I think I've showed you this before, the zoom box feature. You could just do zoom and then zoom in, or zoom box, the first option. Kind of create a box around that region if you wanted to zoom in on that region. We can see that they do intersect. So yes, you can, as long as your calculator is allowed, you can use your calculator to find where they intersect. I do want to show you, because it does work out for this one, if there was a no calculator question where it gave you, in that case it would have to actually give you the graph. So say it gave you the equations and it gave you the graph, but it didn't tell you where the 2 graphs intersected and you couldn't use your calculator to find it. Well, I'll ask you, how would you find where they intersect? Set them equal to each other. So to find where they intersect, so the 2 intersections, you would set these 2 curves equal to each other. So x squared would equal 2x minus x squared, because that could happen on the AP test where you're given the 2 functions, you're given the graph, you need to know where they intersect, but they're not giving you that information. You would have to know how to find it. So I can add x squared to each side, so 2x squared equals 2x. Yeah, I would divide by 2, so x squared equals x. And you could bring, you could use reasoning and figure this out too. I would bring the x over to this side so it's equal to 0, so x squared minus x equals 0, and then factor out a GCF of x. So x times the quantity x minus 1 equals 0, to see that your intersections occur when x is 0 and when x is 1. Okay, so then you know that you're going to have the integral from 0 to 1 of which of these 2 curves was the top curve. The second one was the top curve. So you would have 2x minus x squared and then minus x squared dx, which you could simplify to the integral from 0 to 1 of 2x minus 2x squared. And then, again, treating this as if we didn't have a calculator, to just substitute the integral into it. Antiderivative. So antiderivative of 2x is x squared. Antiderivative of 2x squared evaluated from 0 to 1. If I substitute in 1, I have 1 squared, which is 1, minus 2/3 times 1 cubed is 2/3. And then if I substitute in 0, I'm just going to have 0. So I have 1 minus 2/3, meaning the area of that region is 1/3. Okay, questions on that one? Okay, the third one then, a little different yet. So this one says to find the approximate area of the region bounded by the curves y equals x over the square root of x squared plus 1 and y equals x to the 4th minus x. Again, you're not given A and B, so these two curves must intersect. Then this one would have to be a calculator question, yeah. Okay, so this is the graph of the two graphs. You can see there is a region here where they intersect twice, creates the region that's bounded by the curves. I'm going to zoom in around this. All right, so for this one, there's our region, but intersections. If you were to find them by hand, you would be setting x over the square root of x squared plus 1 equal to x to the 4th minus x. Okay, this would not be a no calculator question because to solve this by hand, that is more complicated. So for this one, this is why it's saying even to find the approximate area, you would have to approximate where they intersect using your calculator. So you'd want to go on to the calculator and do the second trace for the calc menu. Option 5 is intersect, and find the two intersection points. So this appears at 0. You could just double check, make sure the cursor is closer to that intersection point. It does occur at 0. So one of them is at the x value 0. The other one is at about 1.1807757. Now, just like kind of rounding in the middle of a problem, I would not round this if this was a calculator question on the AP test, because they might even give you the two curves. You'd have to graph it, or sometimes they might even give you the graph, but you still have to use your calculator to find where they intersect. Just keep this to as many decimal places as the calculator gives you. So keep all, what does it give you, 7 decimal places? 1.1. keep all of them. I mean, it is an approximation, but it's as many decimal places as you're given. And so then we would have the integral from 0 to 1.1807757 of which of the two curves was the top one. The first one given was the top curve. So it would be the x over the square root of x squared plus 1 minus, and make sure when you're subtracting it would be minus the quantity x to the fourth minus x. So it would really be minus x to the fourth plus x. Okay, and so I want to show you two things. One, like I said, this would be a calculator question, so then you certainly could just type this integral into your calculator. Okay, so let's do that and just get the approximate area, but then I just want to review one thing with you with this example. If you had to do something like this by hand, so math, option 9, FNINT, type in your limits. Is that what you guys got? So approximately 0.785 if you round it to 3. Yes, for the final area you would round it to 3 decimal places. At least 3. If you rounded it to more, that's fine. Just don't round it to less. Okay, I do want to review one other thing with you though. If you had an integral like this to evaluate by hand, looking at the integrand, the expression that you are finding the integral of, would you be able to just find an antiderivative of every term? Or would you need to use something else to find the integral? Just for this integrand, like if you were doing this by hand. Do we know an antiderivative for this first term, for example? Yes, so if you had to do this by hand, I would rewrite, this is just what I wanted to show you, I would rewrite this as two different integrals. So I would rewrite it as the integral from 0 to this number here of x over the square root of x squared plus 1, have that as its own integral, and then minus the integral of x to the fourth minus x. And why I'm splitting it that way is x to the fourth minus x, I can just evaluate that integral, I can find an antiderivative. The very first term though, that first integral, I have to use substitution for. Because we don't just have an antiderivative for x over the square root of x squared plus 1. So that's just what I want to go through with you. You don't have to go through evaluating the entire thing, but just a review of substitution, how you would set this up for this integral. What would you choose for u? The entire bottom? Yes, just the x squared plus 1. So you would still have a square root of u on the bottom. And then du would be what? 2x dx, and we have an x dx. Oh, yep, so we don't have a 2. So 1/2 du would be x dx. So I would have 1/2 in front, and then the integral, the x dx would become du. But I could just write this as 1 over the square root of u, and then du at the end. And then remember this also, your limits would no longer be from 0 to this number. You'd have to make them u values by plugging them into here. So when x is 0, your u value would be 1, so your bottom limit is now 1. And then when x is 1.1807757, your u would be and this I would not round. I'll write this below here. I would keep it at that number of decimal places, so 2.394231.3, so I could round it to just keep the 7 decimal places that I had. Now again, would you have to deal with this by hand? No, because you would be using your calculator to get this anyway. So you would be doing it the way we did it up here. I just wanted to review. Substitution is still going to come up with integrals. So if you had to solve this type of integral by hand, just so you understand the substitution part of it, and then you would keep going from there. Questions on that? Okay, so then there's some practice there for you.